from 1916. And this is a very, very important year for chemistry, 1916. Not only for this, but we have a centenary for something else, which I think has been quite important, the year 1916, and that is Gilbert Lewis published in 1916 his famous paper where he suggested that the chemical bond, which so far had just risen as a line without any physical interpretation, should be identified with an electron pair. Well, in order to honor this, there is a book which appears actually these weeks on structure and bonding, and I wrote one chapter of this. And because I had to write this chapter and I wanted to know something about the history, I read about Gilbert Lewis. And when I read him, I was really amazed. I think most of you have heard about Gilbert Lewis, and you are using the word Lewis electron pair bonding or Lewis acid and Lewis bases. But do you really know something about it? Did you read him? I read all of it, which he wrote, which is not a lot. There are actually only 3 major papers which he ever published on the topic. Gilbert Lewis was an amazing person, and it's worthwhile to reread it. Not only his 1916 paper, but particularly the 1923 monograph, which is out of print, of course, but it's online available from this address. You can get it. You can still read it. And only another paper in 1933 appeared about the chemical bond in a very, very dull tone and a very sad tone, and it ended with the word, I think I cannot really contribute to this topic. Another amazing paper because it did not have a single reference. Gilbert Lewis suggested this electron pair bonding model, and at the same time in this paper, and in particular in this one, he tried to explain chemical structures with this bonding model which we are all using. It's an amazing book because nearly everything is wrong. What's in it? He wrote that double bonds, triple bonds are weaker than double bonds, are weaker than single bonds. He wrote that acetylene has a triplet ground state because it's isoelectronic with oxygen. And at the same time, he had a feeling, this chemical feeling, that it cannot all of it be wrong. Something must be right, and we know that something is right, but he did not really see it. He felt it only. And so he wrote in 1923, something else I have to say. He felt that the answer to this would come from something which at that time just was starting, that was quantum theory. 1923 was not yet 1925 and 1926 when Schrödinger and Heisenberg published their famous work. In 1927, for the very first time, Heitler and London explained chemical bonding in terms of quantum theory. It could not be explained, and he had a feeling that it could come from quantum theory, which in a very primitive way had been suggested by Max Planck. The point is that Gilbert Lewis did not like quantum theory. Like Albert Einstein, he shared his dislike for him. And that comes clear to the fore in his book when he wrote, but since we have been obliged here and there to take cognitions to the entering wedge of scientific Bolshevism, which we call quantum theory. Now in American and Bolshevism, that is something the worst which an American can ever see. And so you can see how strong his feeling was against quantum theory. But I cannot refrain from attempting to forecast some of the logical consequences which must follow from the new facts that have been discovered and the interpretation which they have been given. For me, the true legacy of Gilbert Lewis is not so far the electron pair bonding model. It is not the Lewis pair, the Lewis acid and the Lewis base. Both of them are extremely important. But the very, very final sentence which he wrote in his book, and that is this. First, he wrote, quantum theory has been criticized for furnishing no adequate mechanism, but presumably the root of our present problem lies deeper than this, and it is hardly likely that any mechanism based on our existing modes of thought, and that was he was using, will suffice for the explanation of the many new phenomena which is a study of the atom is disclosing. And now it comes. We should, and these are the very last, sentence in his book, be maintaining an opening of mind so that when the solution of these problems, which now seem so baffling, is ultimately offered, its acceptance will not be retarded by the conventions and the inadequate mental abstraction of the past. And that holds until today. So we should be prepared to be open for new solutions. And Gilbert Lewis himself felt that he was not open for quantum theory, but the next generation should do it. For those of you who feel that their work is not sufficiently acknowledged and they do not get enough citations, this is a list of the citation of Gilbert Lewis. 1916, 3 citations, 2 citations, 1 citation. Then there was an uprising. But this came not to his own work, but to Langmuir. Irving Langmuir picked up the Lewis bonding model himself, and he was the one who recognized that there was something behind it. He published several papers, and he was the one who actually introduced the octet rule. The octet rule is not due to Lewis. Lewis always talked about 2 electrons, never on 8 electrons. And he did not think it was very important. But Langmuir recognized this. And therefore, there is the uprising in the papers. And after this, you see 1 citation at the most. It's very rare that a paper which is published in 1916, 100 years later, has a peak of its publication. This is 2015, this is 2016, but just in May, it will certainly have get more than this. So if you think that your paper will not receive enough citations, you just have to wait for 100 years and maybe it will. So let's do this. Let's keep maintaining an opening of mind. And let's see what we can do with the Lewis model in combination of the old Lewis model and with modern quantum theory. And we start with something which Lewis himself already introduced. He showed that not only the electron pair can be formed in this way, 1 electron from here, but 1 from here, but he also introduced this, the Lewis base and the Lewis acid. And he said already that it's important to distinguish it. This, unfortunately, is forgotten due to Linus Pauling. Linus Pauling did not like it. Linus Pauling devoted his book to Gilbert Lewis, but actually the way how he introduced quantum theory into chemistry is in many ways biased. And he did not use it, and that is one of the reasons that people didn't pay attention to this. Very important is so that we can have 2 types of electron pair bonding, and very important is if you have the same type of atoms, A and B, like here and this, that this one is always significantly weaker than this one. This kind of bond is always stronger than this if you have the same type of atoms. This bonding model is now familiar to people who are working in transition metal chemistry. You see that with transition metal, the bonding model of sigma donation and pi back donation, which carries the name of Dewar and Chutt and Duncanson. It was actually only Dewar who introduced it. Chutt and Duncanson later recognized this, and they introduced it into transition metal chemistry. And when you go to transition metal chemistry, then indeed this bonding model is really ubiquitous. What I want to show you today, that it's worthwhile to look into main group chemistry, not only for explanation, but also for predictions. In order to show you the power of this model, we take 3 simple compounds, basic compounds: carbon oxide, CO2, CCO2, C3O2. What do you know about these carbon oxides? Well, if you take a Lewis structure, you would say that all of them can easily be written like this, and all of them should be stable molecules. Are they? This molecule, CO2, is a rock-solid molecule, and you know that it's a bonding angle of 180 degrees. This molecule does not exist, at least not in this form. There is a very high-lying shallow minimum on the triple potential energy, but this one, not at all. But you can write a stable Lewis structure. This one was already synthesized in 1906, but it took until 2008 before it was recognized that this molecule actually has a bending angle of 156 degrees. Why? What are those Lewis structures telling about it? Can they be used in order to understand this strange trend? Let's go back and let's see how those 2 types of bonding models can be used to explain it. If we start with C2O2, which does not exist at all, if we form it in such a way, the classical Lewis structure with electron sharing bonds, then we have 2 unpaired electron years and 2 unpaired electron years. That means carbon monoxide binds with another carbon monoxide, but both of them have to be excited in the triplet state, which costs nearly 140 kcal per mole. That means for the bonding, in order to form for the bond, you have to invest nearly 280 kcal per mole. That's more than the bond dissociation energy. This system has to invest much more than it would gain, so there is no way of getting an electron sharing bond. Well, what's this one? What about donor acceptor bonds? This is a donor and this is a donor. In order to get donor acceptor bond, you need a donor and an acceptor. There is no vacant sigma orbital here at all, so it cannot form donor acceptor bonds. The electron sharing bonds is energetically unlikely, or not possible, because it's too high. With other words, C2O2 in this linear structure does not exist. And now we go to this one. Now we go to CO2 and to C3O2, and we compare this with this. This is linear and this is bent. Let's first write it in the classical way with classical Lewis structures, and now write the two with, let's try to write the two with donor acceptor bonds, and that is possible because carbon has 4 electrons, 2 electron pairs, and they can donate into the vacancy of the oxygen. Here are vacant orbitals, could have sigma donation and sigma donation, and those orbitals here could make pi back donation. The same as here, with the difference that now the ligands are the sigma donors who could donate into this, if you write it like this, and that this one would make pi back donation. With other words, the donor acceptor interaction is possible in CO2 and in C3O2. Let's again make an energy balance of this. In order to form an electron sharing bond, this carbon atom has to have 4 unpaired electrons, so it must be the quintet S state, and oxygen the triplet pi. Here also the oxygen is the quintet S state, and the CO ligands must be in the triple pi state. If we go to the dative bond, this carbon would be a single D, and the oxygen also a single D. The carbon would be a single D, and the CO would be a single D. This is the ground state, and also this is the ground state. All others are excited states. So let's see how much energy we have to give in and how much energy we would get out from the bonding. And here are the values. In order to get for the quintet S state, you have to pay 96 kcal per mole. In order for the singlet D state of carbon, 29, and for the singlet state of oxygen, 45. For this triplet state, 139.3. And now we see if it's worse or what the different bonding situation would give you. If you make an electron sharing bond, then you would have to excite the carbon atom to the quintet S. The quintet S costs 96 kcal per mole. Oxygen is in the ground state. In this case, carbon would have 96, but the CO have to be excited 2 times 139 kcal per mole. The excitation energy in order to bring it into this situation is 375. For the donor acceptor bonds here, carbon in the singlet D, oxygen in the singlet D. Carbon in the singlet D, that costs us 29.1, and oxygen in the singlet D 2 times 45, altogether 119.9. That means for the electron sharing bonds, the investment is 96. For dative bond is 120, but dative bonds are weaker than electron sharing bonds. There is no reason why this species should engage in dative bonds. It makes classical electron sharing bonds, and this value is easily surpassed by the bonding interaction. If we go here, we see that those 375 is far too high to get 2 double bonds. But for donor acceptor bonds, we just have to excite by 29 kcal per mole. This is surpassed by donor acceptor interaction, and that means that CO2 binds to electron sharing bonds, but C3O2 binds to donor acceptor bonds, a different bonding situation in this molecule over to this. And this agrees with the calculated bond dissociation energies. And they are given here. If you dissociate CO2 into carbon and oxygen atom, you have a dissociation energy of 376. That means each bond 188 kcal per mole. This, by the way, is much higher than what you have to invest. 188 kcal per mole. That is a reasonable value for a double bond. Here, if you dissociate it into carbon and two COs, it's 136. For each of the bond, only 68 kcal per mole. This double bond, formal double bond, 68, that agrees with dative bond, this 188 with electron sharing bond. These bonds are always significantly weaker than this. And that means that C3O2 is actually a complex between a naked carbon atom, which has two unpaired electron pairs, and the donor-acceptor interaction. And the explanation for the bonding angle, and now we jump into transition metal chemistry, comes from the fact that the sigma donation is quite strong. It's usually stronger than the pi back donation, and the bonding angle depends on the strength of the pi back donation. And if the ligand becomes a better pi back donor, then it widens, and if it's a poorer pi back donor, then the angle becomes more acute. And this actually was the reason which we studied. These kind of compounds with different ligands, L the name was given by us, are carbones. They were recently also translated into the Chinese, and we published this for the first time this in 2009. And these are carbones, and when a CO is substituted by a phenyl group, by a phosphine group, which is a significantly poorer pi back donor, you see what happens with the angle from 156 to 145, and if you have two of them, 132, this is a famous carbodiphosphorate by Ramirez in 1961, always described as a double ylid, but this trend of the bond angle nicely explains why we have it at this bonding model of donor-acceptor interaction, really nicely explains why we get this. The potential for linearization is very, very weak. It takes just 2 kcal per mole, and that is the reason why in the solid state, carbon suboxide becomes linear, because those 2 to 3 kcal per mole are easily given by interaction. Well, with this knowledge, we started with the carbon chemistry and looked for predictions, something new. And we have realized that phosphines, which came from transition metal chemistry, are similar ligands as N-heterocyclic carbenes, which were introduced by Arduengo. It should be possible to substitute a phosphine by a carbene. That would give a carbon-carbon donor-acceptor bond. And that was published by us and predicted in 2007, carbodicarbene. 1 year later, Guy Bertrand isolated the first carbodicarbene, and this is now a class of compounds which is under active research, because these molecules are by themselves very good catalysts. But this is a point I will not talk about today. So carbodicarbene were the first, but not the last class of compounds which we predicted and which has been made. We also could show that since they have two lone pairs with a double Lewis base, that they can bind 2 Lewis acids, and that was done by Petz, who could bind 2 boranes. And Alcarazzo showed if you have then a Lewis acid which has 2 empty places, like BH2+, you can isolate it as well. All of this work has been summarized in a review which appeared 2 years ago. Now, this is a carbon, and now we go into theoretical chemistry and analyze the chemical bond in a little more detail. And nowadays we have quantum chemical methods around which can say something about the donation and back donation in a quantitative way. So let's first write those 2 lone pairs in a better way. One of them has sigma symmetry, the other one has pi symmetry, and then there are 2 vacant orbitals. This is a vacant one, and this is a vacant one. And those ligands can now donate. They have 2 lone pairs. The plus-plus donation fits by symmetry into this, and the plus-minus donation fits by symmetry into this. So it can nicely donate into this, and this actually can, to a certain degree, back donate, and if it's a poorer back donor, it remains as a lone pair, and this is the other lone pair. But this, with modern methods, can be done in a more quantitative way with the energy decomposition analysis, which was introduced by Morikuma and also by Tom Ziegler. I think that is best known to most of you. You are interested in a chemical bond between two or more fragments, AB. You calculate those fragments and you superimpose the frozen densities, calculate the energy, and you superimpose it in the equilibrium geometry. The energy difference from here to here gives you electrostatic interaction. You take care of the Pauli repulsion. You just make an antisymmetrization and renormalization from here to here. That gives you the Pauli repulsion. And now you let the orbital relax from here to here. You get the orbital interaction. And this can be broken down into pairwise contribution. That was introduced by Michalek and Mitorai, who worked together with Ziegler. So the energy change, the change in the electron density during the bond dissociation, due to the bond formation, can be diagonalized. You diagonalize the density matrix, and then you get pairwise contributions for this. And these pairwise orbital contribution also have an associated energy term. The mathematical details can easily be rounded this. I just want to show you what the results of these are. For example, and you have carbon with the phosphine groups, which were known, and then with an N-heterocyclic carbene, which we had predicted. And those two ligands were suggested to have very similar properties. How does it show up? Well, the total interaction energy here is stronger. That is known. It's a stronger bonded one. These are the very large terms of the Pauli repulsion. This is an electrostatic attraction, 30%, roughly 30%, so about the same. And finally, the orbital attraction, which is given here. And now you can break it up into the plus donation, into this one. That is this one, 60%, 62%. Into the plus minus, that goes into this orbital, 30%, 34%. And finally, the pi back donation from here to the ligand, and you see 10% and 12%. Very, very similar values, which means that indeed those two ligands behave very, very similar. But this can not only be put into numbers, but also in figures. These donations, this plus-minus donation, for example, those charge donations, those deformation can be given. And now these are not orbitals. So now the colors show areas of charge donation and depletion. And the trend is from red to blue. It goes from the red to the blue. This is the plus one, and this is the plus minus one, so from red to blue. This is the pi orbital here, and this is the formerly empty orbital here. And this finally is the back donation. Now you see from the carbon to the ligand, from the red to the blue, and here are the associated energies which are given to this. This is with the triphenyl phosphine, and here's exactly the same with the N-heterocyclic carbene. So donation from red to blue, and the back donation from red to blue. So you do not only get numbers for this, you also get figures for this. Well, we did in the last 8 years or so a lot of work, and I just want to show you what we did recently, because it is still an ongoing project which has new surprises. We looked at the variation of ligands L. I just gave you an example for this. The reactivity of two lone pairs, I mentioned it shortly. Variation of the central atom. Is this restricted to carbon? Could it go to other atoms? That was totally new. Absolutely no compounds of this were known. So with the variation of compounds, we jumped into this. Could you find the same type of molecules with silicon? And here's an interesting story which I want to share with you. It's about silylane and silylone. Silylane is the silicon analog of a carbene, and silylone is the silicon analog of a carbone. The story begins in 2009 when Herbert Rösky, with whom we are now cooperated, found out that silicon dichloride can be stabilized by an N-heterocyclic carbene. We had calculated this compound, and this was a paper in 2009, and that made some headlines because silicon dichloride to silicon 2 so far had not been isolated before. What brought us into the game was when he contacted us because he wanted to substitute the N-heterocyclic carbene, the Adoenko carbene, by the so-called CAC carbene, which was isolated by by Bertrand, which has only one nitrogen. Here we have two nitrogen. The double bond is not that important. Here you have only one. Because there's only one nitrogen, it's a stronger pi acceptor, therefore it binds the stronger, and therefore this should even have a stronger bond. And indeed, we calculated and found that this bond is indeed now shorter than the one before, 2.037. It should be 1.949, and the bond should be stronger, 42 kcal per mole. So he runs the reaction where he took this molecule and let it react with this carbene and expected a one-to-one replacement. What he found was totally different and unexpected, and that was actually the reason that he contacted us. He took this complex and let it react with this. And rather than a one-to-one reaction, he got a one-to-three reaction. One of these new ligands, these carbene ligands, took one of them out and they dimerized, giving this one. This was not so surprising. The most surprising thing is that actually two of those two ligands bind now to the silicon. Not one, but two. And when we look at the structure, and you see calculated and experimental one in nearly perfect agreement, that this bond is even shorter than we had calculated with only one of them. This bond is over 1.85. When you have only one and a lone pair, it's 1.95. But there should be a lone pair at the silicon. There's no place for a second ligand to bind. How could it be possible that silicon binds two of them and that they have such a strong short bond? So we looked at it. The silicon dichloride, which binds with these N-tetracyclic carbenes to this type of dative bonds. There's a second possibility. When you want to make shorter bonds, you must make here electron sharing bonds. That is done here. When you have electron sharing bonds, that means that one electron goes to here and one electron goes to here. So when you have those two electrons distributed over those, you have one electron here and one remains here. And the second one is the same here, one electron sharing bond here